Well, hello, physical science class. Hope that you're doing well during our extended time apart. Pray that you guys are all safe and getting used to learning kind of in this different environment now. I'm getting a little bit more used to it, although I miss seeing all of your guys' joyful faces. Well, here we are in Chapter 17 of Physical Science. We're going to be looking at sections A and B today, and then next week we'll look at sections C and D together. We're getting kind of an introduction to chemistry so that we are all the better prepared for chemistry when you jump into that either next year or the year thereafter. So section 17A provides us with a brief history of the elements. Now, an element is any pure substance that is made of only one kind of atom. That is our definition of element. And one of the difficulties that those who went before us had in trying to identify the elements and what everything is made up of is that a lot of things, as they come to us naturally, are already combined with other things. And so much of the work of chemistry in its earliest phase is trying to isolate apart the constituent parts of every material that is around us. And a lot of things that we look at are actually combinations of elements in compounds or molecules. And so we're kind of seeing the history of that development here together in these slides. So the earliest known elements, the ancients knew of at least 9, and all of them were solids. But the Greeks, when they came along, started to talk about what were all of even these things made up of. And their idea was that there were actually 4 elements that made up everything. Air, fire, water, and earth. And you kind of see in this little chart here to the side that in this corner you'll see the word hot, and in this corner you'll see the word cold, you'll see wet here, and you'll see dry here. And so the idea of each of these 4 elements was that the hot and dry, when that comes together, you get fire. When you have dry and cold, you have earth. When you have cold and wet, you have water. And when you have hot and wet, you have air. Now, there was then discussion, these are the 4 elements, or the 4 essences that everything was made up of. Then there was a discussion of a 5th essence, or a quintessence, that might be behind all of these things. And so there was always this kind of study and look for the quintessential thing, the thing that made up everything else. So you kind of fast forward from the Greek philosophy regarding the elements then to alchemy, which is the transition point from the ancient times of studying science towards a more modern view. The alchemists are famous for the amount of apparatus, the kind of equipment that they put together to try to study and look at the world around them. But they started to do further studies into what is everything made up of, and they made some progress. In the 17th and 18th centuries, you have a couple of notable individuals that you should be aware of. Isaac Newton and Robert Boyle are considered kind of the predecessors to modern chemistry. Robert Boyle for sure being that. One of his most famous works is The Skeptical Chemist. Notice the spelling there is a little bit different than we would spell it now in English, but that work in 1661, Robert Boyle is thought by many to be like the father of modern chemistry. And then a man by the name of Antoine Lavoisier, a Frenchman who, again, did a lot of work in chemistry and isolating elements and learning more and more about the world around us. He broke down water into hydrogen and oxygen, was able to determine that those 2 elements actually make up water. So the history of the development of the periodic table demonstrates the process of model making in science. Remember, we've talked about that in science, you're trying to produce models that help explain the world around us. And as long as they actually explain the world around us, those models are upheld, even buttressed by further studies that have been done. But whenever there are outliers that don't fit into the present model, at some point in time, they start to discuss whether or not the model needs to be replaced by another model. And certainly this can be seen to be the case when it comes to the development of what we know today as the periodic table. It went through many different models to get to where it is today. So as I mentioned Lavoisier a moment ago, he published a list of 30 substances that he called elements in 1793. Some of his elements, though, as we now know, were compounds. Remember, I told you at the beginning that one of the tricks of getting down to what are the elemental building blocks of all of matter is understanding that a lot of the elements that you're looking at or things that you're looking at to start actually need to be broken down further into their actual constituent elements. It's like saying water is an element. Well, it's not. Remember what we came to find out, that water is made up of two distinct elements, hydrogen and oxygen, in a ratio of 2 to 1. So Lavoisier, some of the elements, even though he did break down hydrogen and oxygen from water, he understood that one. There's some of the elements that he pointed out that actually were themselves compounds that would later be discovered to be compounds of different elements. So by the end of the 18th century, around 32 of the modern elements had been identified. So Dalton eventually documented as many as 60 elements, and he came up with a complex symbol system that no one adopted. It looks something like this. And you can kind of see, if you look closely at how these symbols are, this is definitely does not look like the modern periodic table. Here hydrogen is a circle with a dot in the middle of it. Zinc is a circle with a Z inside of it. So there's different things here. And then you notice that when he starts to put things together, you start like arranging them like this. This symbolic notation, while he thought maybe it was quite clever, it never really was not taken on by a lot of people. Now, Berzelius made his own elemental notation, which was quickly accepted by most European scientists, and it's very similar to what is used today. Imagine the difference between looking at symbols something like this, where you have these are actual symbols that were being used. Again, remember, glass is not an element as we know it today, but again, this is part of the development of the periodic table. But neither is formic acid a element by itself. But carbon would be, copper acetate would not be. But so again, you see the kind of complex symbols, this versus this. There's copper sulfate, ammonium. Notice that these symbols look very, very similar to what we would do today. One of the biggest differences with Berzelius' system is that he had a penchant for putting them as superscripts above, whereas today, instead of putting these numbers above, we put them down below. So other than that, though, you see a striking resemblance between his system and what is being used today, because today's system is largely based on Berzelius' beginnings of a system for elemental notation. When Berzelius died in 1848, there were 57 known elements. So we see that more and more discovery of elements is happening over these years. Today, we know that there are at least 118. Now, a few of the very top ones haven't been officially named yet, so they're given names like ununoctium or unumpentium, but otherwise, a lot of those are being named and being discovered. So chemical symbols today are 1 or 2 letter symbols, except again for those very top ones, those very, very high numbered ones, which are being manufactured in like atomic reactors or colliders. Those ones sometimes have 3 letters, but that's just because they don't have an official name yet. But all official named elements have 1 or 2 letters derived from the element's name. Some come from the Latin name, but then those temporary names, as I mentioned, are the ones for those 3-letter ones that happen that are still being discussed, the actual naming of them. These symbols always have a capital letter, so if there's only 1 letter, it's a capital by itself. If it's a 2-letter symbol, the first letter is capitalized and the second is not. Let's look at an example here of uranium. Note here, uranium found on the periodic table is number 92. The atomic number is right there. The atomic number, by the way, is the number of protons in the nucleus. Uranium, the name is listed. In this case, we see the symbol of radioactivity up here in the top right corner. The symbol itself is just U, capital U. The atomic mass is 238.0. So we have the mass being listed underneath the symbol, and the number of protons or atomic numbers up here. So this is atomic number, and this is the atomic mass. And then below that, you have electron structure by energy level. Again, something that we won't be talking about here today, but This is just a description of where the electrons are by energy level around the nucleus. Now, the transuranium elements are every element beyond 92, beyond uranium. That's why they're called the transuranium. They're beyond uranium elements. And these are produced only in nuclear reactions. And we have discovered elements up to 118, although some yet are not confirmed. So like I said before, there's some that are still not been confirmed, but they do exist up to 118. But in nature, they only exist up to number 92. So you can't find anything beyond uranium in nature. The rest of them are produced only in nuclear reactions. So at room temperature, though, of the 92 naturally occurring elements, 11 of them are gases, 2 of them are liquids. Mercury is probably the one that you're most familiar with in this regard, but also bromine is a liquid at room temperature. And the rest of them are all solids. So you have 11 gases, 2 liquids, and the rest are solids at room temperature. Only a few elements occur as single atoms. In other words, a lot of elements, as you find them in nature, are found either, so it's monatomic if it's found by itself. The noble gases are a good example of that, like neon is a good example of this, or xenon. Those are noble gases, and those you do find by themselves. There are a couple of examples of things that you find as monatomic elements where they're only one atom, single atoms, but otherwise a lot of these things exist as diatomic. So oxygen gas, for example, is actually O2. Hydrogen gas is H2. So oxygen bonds to itself, hydrogen bonds to itself, so we normally find those as diatomic atoms. And then there's a whole lot of things that exist as molecules or compounds. A lot of the elements that are found in the Earth's crust are actually compounds of several different elements combined together. So for example, if you want to get pure aluminum, the way you have to get at that is by taking it out of bauxite, which is a combination of elements in which you have to refine the aluminum away from the rest of the elements that are present there if you want to have just aluminum by itself. All right, so let's now talk about 17B, the periodic table. Oops, wrong element. You see how important it is that we know which element is which and being able to distinguish them one from another and to understand the properties and qualities of each element. So how do we go about organizing the elements? Well, initially it was necessary to memorize the various properties of all known elements. But several scientists started to pick up on similarities between the elements. So there's some elements that were behaving in similar ways as other elements. And this fact, this observation, led them to start grouping the elements into different categories. Dobereiner is one of the first to do this. He created a list of elements based on triads. A triad is just a group of 3 elements with similar properties. And so as he's looking at various elements, he's seeing groups of 3 that seem very similar to one another. But the problem with the triads was that soon more elements were found. And there would sometimes be more than 3 similar elements in one group. So his triads idea was good as far as it went, but the problem is we find some that go beyond even the rule of 3. Like I found 4 elements that are similar to one another, or 5 that are similar to one another. Here's a couple of examples where he found like alkali formers and salt formers, and he put them together and saw that these were things that were similar to one another. Well, John Newlands arranged elements by atomic mass, and he observed the law of octaves. He recognized that every 8th element repeated properties. Just kind of like in music, if you go up 8 steps from one note, you get to that same note just 1 octave higher. So if you start at middle C and you move up 8 keys, 8 steps up, you get to another C. And so he found the same principle within the elements. And he was able to include the transition metals also in his discussions about this. Then comes along Mendeleev, who developed the periodic table by arranging elements by atomic mass, just like Newlands did. But he left blanks where properties or mass did not fit. And through these blanks, he started to predict the sorts of properties that should be found if that element was found. And this truly was incredible. This is when you start to realize that someone's on to a really good model. When the model not only is able to explain present phenomenon, explain the things that we already know, but to make educated guesses about things that we don't know, things that have not yet been discovered. So Mendeleev was able to make some highly specific guesses about elements that had not yet been discovered or isolated by themselves. And he could say, these should be about the properties that we find from those elements once we find them. And sure enough, we found exactly that. So Mendeleev's table, his periodic table, really did form the basis for what we see today in the modern periodic table. You'll see here on the chart here to the side that there are some differences, but he did create kind of the first working periodic table, and he had a huge amount of predictive power, which really give a lot of credit to his model. But some elements were out of order when positioned by atomic mass. So remember, he's just adding all of these, he's putting them in line depending upon the mass of the atom. So along comes Moseley, who changed the order of the periodic table to follow that of atomic number, the number of protons, rather than just the total mass of the elements. And in some cases, this would switch the ordering of the elements, where even if one had a higher number of protons, it might have had a lesser atomic mass because there was more neutrons in the nucleus. And because of this, sometimes the order would be different. So when he arranged them on the order of atomic number, which is the number of protons, rather than atomic mass, which is really the addition of protons plus neutrons, when Moseley made this rearrangement, things really started to fall into place. And so the periodic law is that properties of elements vary with their atomic numbers in a systematic way. And with that, I think I'm ready to introduce you to a very important tool, what is considered a pal of all chemists, and such a momentous occasion must be accompanied by musical fanfare.
And now, ASAP Science presents the elements of the periodic table.
There's hydrogen and helium, then lithium, beryllium, boron, carbon everywhere, nitrogen all through the air, with oxygen so you can breathe, and fluorine for your pretty teeth, neon to light up the signs, sodium for salty times,
Magnesium,
aluminium, silicon,
phosphorus,
then sulfur, chlorine, and argon,
potassium,
and calcium so you'll grow strong,
scandium,
titanium, vanadium, and chromium, and manganese. This is the periodic table, noble gases stable, halogens and alkali react aggressively. Each period will see new outer shells while electrons are added, moving to the right. Iron is the 26th, then cobalt, nickel coins you get, copper, zinc, and gallium, germanium, and arsenic, selenium, and bromine film, while krypton helps light up your room, rubidium, and strontium, then yttrium, zirconium,
niobium,
molybdenum, technetium,
ruthenium,
rhodium, palladium,
silverware,
then cadmium and indium,
tin cans,
antimony, then tellurium, and iodine, and xenon, and then cesium, and barium is 56, and this is where the table splits, where lanthanides have just begun, lanthanum, cerium, and praseodymium. Neodymium's next to promethium, then 62, samarium, europium, gadolinium, and terbium, dysprosium, holmium, erbium, thulium, ytterbium, lutetium, hafnium, tantalum, tungsten, then we're on to rhenium, osmium, and iridium, platinum, gold to make you rich till you grow old, mercury to tell you when it's really cold, thallium, and lead, the bismuth for your tummy,
polonium,
astatine would not be yummy,
radon,
francium will last a little time,
radium,
then actinides at 89. This is the periodic table, noble gas is stable, halogens and alkali react aggressively. Each period will see new outer shells where electrons are to the right. Actinium, thorium, protactinium, uranium, neptunium, plutonium, americium, curium, berkelium, californium, isonium, fermium, indolium, nobelium, lawrencium, rutherfordium, wm, sprigium, boreum, hesium, meitnerium, dubsinium, mercenium, copernicium, natrium, flerovium, pentium, livermorium, septium, noctium, and then we're done.
Okay, so I hope you enjoyed that. I love that little song. That is one way in which you can go about trying to memorize elements from the periodic table, and I actually challenge you to memorize the first 10 this week. I think it would be a good exercise for you to attempt to do that. You can do it just by learning the very first 10 from that periodic table song, right? There's hydrogen and helium and lithium, beryllium, boron, carbon everywhere, nitrogen all through the air, and oxygen so you can breathe, and fluorine for your pretty teeth, neon to light up the sign, sodium for salty times. So notice that you can just remember a song like that, and that might be a good memory tool. But I'm going to show you another one here in just a moment. But before I do, let me just show you the periodic table. Now note, this looks a little bit different than the other slide you just saw, and that's because these intertransition elements, the ones that are right in here, actually start here with lanthanum and actinium. These guys are usually put at the bottom of the chart. These guys are put at the bottom because notice how wide the chart has to be in order to include those. So usually what you see is what you'll see on the next slide. You see the lanthanide series and the actinide series are put at the bottom of the table so it's not so wide. So this is what you normally see, where the lanthanides and the actinides, your actinide series and the lanthanide series, they're called lanthanide because they come from the La, your actinide because they come after actinium. So these two guys are usually found here at the bottom of the periodic table, but they would otherwise fit right in there where the table splits. That's what they're referring to in the song that you just heard. But notice here that things that are under the same column on the periodic table have similar properties. So when Dobereiner sees his triads and sees things like lithium, sodium, and potassium and groups them together and says that they're similar to one another, they are. It just so happens that there's also other elements that are similar to those as well, because they all land on this first column. Everything landing in the second column are similar. These are called the transition metals. Everything in this yellow block have similarities to one another, but even the things, again, in their respective columns are even more specifically similar to one another. And again, then you continue all the way to the other side of the table. Each column demonstrates unique properties, but those unique properties, you usually find them to be similar within a column. So the challenge here is going to be to memorize the first 10 elements. And like I said, you could do that just by memorizing that song. You probably could just sing that a few times and you probably have it down. But I'm going to show you another quick method towards memorizing the first 10 elements that I think you might find is fun. And it's something you could apply when you're trying to memorize something else as well. It's called memory pyramiding, or providing a structure of pictures in your mind that help you remember various things. So the idea whenever you memorize in this way is to try to come up with a very creative and a vibrant way of remembering something by putting together a really good story. So here we're going to try our best. I'm actually taking this from a book that talked about how to memorize the elements of the periodic table, and it goes through like the entire periodic table. I'm just going to look at the first 10 and show you it through PowerPoint. So if we're going to memorize the first 10 elements of the periodic table, this is how we're going to go about it. We're first going to imagine that entire periodic table wrapped around a fire hydrant. And the reason you're going to do this is because when you see the hydrant, you're going to remember hydrogen. So imagine the periodic table in its entirety is wrapped around a fire hydrant, and you're going to remember the very first element on the periodic table is hydrogen because of that hydrant. Now imagine that the hydrant is actually attached to a massive helium balloon. And this helium balloon is so massive that it's able to rip the hydrant out of the ground and start pulling it up into the air. So you remember this balloon, and you're going to remember helium, because you know that helium is lighter than air. It wants to float upward, so helium is lifting this hydrant up into the air. Well, all of a sudden, the helium starts to, the balloon pops a little bit, and it has a little bit of a hole, and so some of the helium starts escaping out of it, kind of wisping out of the balloon. But you're also going to remember this particular balloon happens to have a lisp, and so you're going to hear it going not s, but f. And as you hear that sound, you're going to think of lithium, lithium, lithium. Well, this lisping balloon, as it's traveling upward still, attracts the notice of a traveling bee, who looks at this balloon and thinks, that looks really yum. And you're going to remember from that, beryllium, beryllium. The bee sees the balloon and sees it to be really yum and thinks, beryllium, really yum. And you're going to remember beryllium. Yeah, okay, I know. It's a little cheesy, but just go with me. Usually the more cheesy it is, the more memorable it will become. So along this bee flies towards the balloon and lands right on the top of the balloon and decides to really dig in, but decides to use its stinger first to bore onto the balloon. And so you're going to remember boron as this bee bores onto the balloon. Well, the moment that the bee bores onto the balloon, we know what happens, right? The balloon pops and the hydrant starts falling out of the sky, and it falls down onto an army jeep that happens to be on the ground, and a huge explosion erupts, and the people that are standing nearby go, car bomb, car bomb. And you're going to remember carbon from that as they shout out, car bomb. Well, no one was actually injured in this accident because the man who's normally driving that army jeep was actually a general, and the general was out that night on his nightly row. So here we have the night rowing general, the night row gen, and you're going to remember, you guessed it, nitrogen. The night row gen. He's out there on his nightly row, and you're going to remember the nitrogen. Well, he rows exceptionally hard, and so he starts to lose his breath, and so he needs to get some oxygen. So he gets an oxygen mask and puts it over his face. And so you're going to remember the next element is oxygen. But then suddenly, as this is still going on, he notices that some sort of paste starts coming out through the mask, and he starts to like pull it off of his face, and he's like, what's going on? And he notices it tastes minty, and it tastes kind of like fluoride toothpaste. And you're going to remember fluorine from this. Fluorine. And not only is this toothpaste filled with fluorine, or fluoride, but you're going to remember fluorine. But also, as he starts to look at his teeth in the glow of the moon on the surface of the water, he notices that his teeth are glowing. They're glowing neon bright. And you're going to remember the element neon. All right, so there's my little story. Now the challenge is, can you tell me the first 10 elements from that story? And if you need to, you can back this up and listen to me tell the story again. But I want to see, can you do it from the story that I just told? Remember, we started off with a periodic table wrapped around a hydrant, and you're going to remember hydrogen from that. You remember hydrogen, the hydrant, was attached to a big, massive balloon filled with helium. And the helium started to carry the balloon up into the air. But after a little while, there was a little bit of a hole in the side of the balloon, and it had a lisp. So you're going to remember lithium. And remember, when this sound starts going off, it attracts the attention of a flying bee. And the bee looks over, he goes, ooh, that looks really yum. And you remember beryllium from that. The bee flies over to the balloon, gets on the top of it, starts to use its stinger to pop the balloon, and it starts boring on the balloon, boron. The balloon pops, the hydrant falls out of the sky, lands on an army jeep, makes a huge explosion, and people say, car bomb, and you're going to remember carbon. But remember, no one was hurt in this horrible accident because the general that drives that jeep was out on his nightly row. And so we remember nitrogen. Remember, he works so hard that he gets out of breath and he needs oxygen. And into that mask that he's breathing oxygen, all of a sudden he feels something on his teeth and he thinks of it's like fluorine toothpaste, but you're going to remember, or fluoride toothpaste, but you remember fluorine. And then from that, he looks at himself in the night water from the glow of the moon, but he doesn't even need it because his teeth are glowing neon. And there's the 10 elements in their order. So there's many ways in which you can go about memorizing things, but I think this is just a fun way to go about memorizing the first 10 elements of the periodic table. I want you to try this on your own as a good challenge. You maybe want to see if you can make up your own story for the next 10 elements and go up through 20. Anyway, see how many you can do. But I hope you guys are doing okay. Stay safe. I look forward to talking to you guys again next week. You have homework assigned on iGrade to get done, so make sure you get those things done. No tests this week. And I'll see you guys next week for the second half of this chapter. God bless you guys. Bye-bye.